Good evening, everyone. We'll now make a start with tonight's lecture. So the theme that we've been going through quite recently has been integrals. So two weeks ago now, I introduced you to the notion of integral. It's a way that we can find areas underneath the curves, and generally it's a method that you use to undo derivatives. So we talked about single variable integrals 2 weeks ago, and I gave you a list of different techniques that you should be aware, that you should know about in your studies, because it helps you to actually explicitly integrate certain functions. Last week, after the quiz, we then used the theory of single variable integration to study probability theory. And it turns out that this is something that Yoni really wants you to do, in that almost every single question in the assignment has to do with using integrals to study probability theory. So I hope you enjoy those questions, because, well, it's probability theory. It's quite relevant to data science. What we're going to do this evening is use some of the theory of single variable integrals and try and extend it to the multivariable case. So I'll explain what I mean by that shortly. But for the moment, I just want to remind you about what we've actually been doing. So the basic idea here is that we have a function. That's too thick. We've got a function f of x defined on some closed interval a up to b, and we want to rigorously define the area under the curve. And the way we do that is by first choosing a partition. So we go x0, x1, x2, x3. Although, of course, a lot of the integrals you'll be looking at will require you to take partitions much finer than this. On each of these three subintervals, you pick a representative point. Let's call it x1 star, x2 star, and x3 star. You look at the height of the function at these 3 points, and you say, I reckon that the height of the function at these 3 points is quite representative of the height of the function in a neighborhood of these points, in fact, all the way up to the subintervals we're interested in. And I'm going to say, well, I know how to find the areas of rectangles, and so the area underneath the curve should approximately be the same as the sum of the areas of these 3 different rectangles. Now, that's just an approximation. The actual area underneath the curve is defined by taking limits. So we take the limit as n approaches infinity. Well, the question you have is, what does that mean? Because I haven't really defined n anywhere. Well, n is basically a parameter which controls the maximal size that these intervals can take. As n goes to infinity, we expect that the maximal length of any one of these intervals shrinks. And so necessarily we get infinitely many of these intervals. We take limits, and that's supposed to give us the area. Now, what we're focusing on this evening is extending this idea to multiple variables. I guess specifically we'll be focusing on the case of 2 variables. And the reason for that is that if you've got a function of 2 variables, then it's not area underneath the curve anymore, it's volume underneath the surface. And this is something that we have an intuitive idea about, and so can make, I think we can make good progress towards actually constructing a good theory of that. So this is the question here. Let's say we've got a function f of x, y, and let's call z the parameter which controls the function. So if we graph this function, what we end up with is a surface. If you've got a multivariable function, then if you graph z equals f of x, y in the x, y, z plane, then what you end up with is a surface. And the question you have to ask is, how do you rigorously define the volume underneath the surface lying above some rectangular region R? I mean, in principle, it could be any region, but it's good to start with rectangles. Now, you can probably imagine exactly how you would do this. You would break you would break your rectangle up into smaller, in the one variable case, we break up into subintervals, but in this case, we break up into tiny little rectangles. And we say that for each of these rectangles, I'll pick a point inside this rectangle and say that the height of this surface on this square here is largely represented by the height of the function at this specific value there. And so that's good because I know how to find the volume of a prism. So this is exactly what we're dealing with here. We've got a prism, this is X, this is Y, and this is the height. I know how to find the volume of this rectangular prism. I just have to multiply the 3 dimensions together. And that should give me a volume contribution over this specific interval. Oh, sorry, not interval. Over this specific sub-rectangle, let's say. So in principle, you do this by taking the interval AB and dividing it into subintervals, and you do the same thing for C and D. The result is a collection of rectangles, and you find the approximate volume contributions for each of these sub-rectangles, and you add them together. And in principle, that should be close to what you actually expect the volume underneath the surface would actually be. So this is all I'm going to say here. Volume can be approximated, so at this stage we're only approximating, by picking a candidate, a representative point in each of these sub-rectangles. And you would say, well, I expect the total volume to be the sum of all of these approximate volume contributions. Now the question would be, well, these are approximate volume contributions. How do you actually get the integral from that, this multivariable integral? And of course, the answer to that is by taking limits. Now, before I get into the actual definition, I'll just point out that even though in this particular picture we're dealing with rectangles, we could also do this for like any other region. All we'd have to do is, divide it in any number of crazy ways. I mean, you can sky's the limit in terms of how you can break your geometry up. But for simplicity, it's good to stick to rectangles. Okay, we're now in a position to define the volume integral. Now, you shouldn't really be surprised how this is defined, because at the end of the day, it's the exact same procedure as before. I've got approximate volumes. I find the actual volume by taking limits. So this is why we need limits in the first place, more or less. Okay, let f be a continuous function. So it is possible to integrate functions that are discontinuous. And you might say, well, of course you can integrate piecewise continuous functions, but there's an even more general class of functions that you can integrate, but we're not going to talk about that in this course. We're going to assume that f is continuous, or at least piecewise. Can't spell. Piecewise continuous. Now, by piecewise continuous, I basically mean that you can break your domain up into finitely many pieces so that your function is continuous on each of those different domains. May have jump discontinuities between the two of them, but between multiple subdomains. Okay, we've got a continuous function in some region in R2. Now, keep in mind that you can do this for any dimension, but it's hard to visualize it if you're not in dimension 2. So we'll stick to dimension 2 for the moment. The volume is defined to be this. The limit as m goes to infinity and n goes to infinity of the sum of all of these volume contributions. Now remember, m is the length of the y subintervals, and n is the length of the x subintervals. So we need to make sure that the rectangles are shrinking in both the X and the Y direction, and that they shrink to 0. And then in that case, the total volume is found by taking the limit in this particular case. Now, what is the volume? Well, this is a multivariable integral, and so we can denote it as follows. Integral, R is the subscript to denote the fact that we're integrating over the region R. F of x, y, dA. dA is sort of shorthand for dx times dy. So dA, that's sort of an infinitesimal change in area. So that area, because we're in 2D here. And of course, area is equal to change in x times change in y. So that's why dA is there. Some more advanced calculus books won't actually use two integrals. They'll just denote this with a single integral over the domain R. But for us, we'll use both. We'll use double integrals just so we remind ourselves that we are actually performing an integral in 2 dimensions and not just 1. Okay, now we've now defined volume integrals, and so you may guess what's coming next. We've got to describe properties of this volume integral to sort of reinforce in our heads the idea that this definition does match up with our intuition about what volume should actually do. First thing, if I'm looking at the volume underneath the sum of 2 surfaces, then that should be the same as the volume under one plus the volume underneath the other. Now, of course, remember, if F and G change signs, then strictly speaking, what we have is not volume underneath the surface anymore. It's a source of weighted volume according to whether or not we're above or below the XY plane. But in any case, we still have this, typo, plus or minus, the integral of plus or minus f plus or minus g is the same as the integral of f plus or minus the integral of g. Okay, another one that we should be familiar with. I haven't really specified what the region is, so let's just call it R. If I take a surface, z equals f of x, y, and scale that surface by the number c, then when we're performing the integral, we're allowed to just put that scaling out the front. So that's nice. Now, here's an interesting one. If R1 and R2 is a partition of R, then the integral of f over that region R is the same as the integral of f over R1 plus the integral of f over R2. Now, I wanted to ask you guys a question, because at least in these units, I haven't really defined what a partition, haven't really defined explicitly what a partition of a region is. So I wondered if I could just ask you guys, please respond in the chat if you can, to explain to me what are the 2 defining properties of a partition. So if I have a set R, and I have 2 other sets, R1 and R2, and I claim to you that this is a partition, what does that mean about the relationship between the sets R1, R2, and R? Any ideas what I need for this definition to work out? Yeah, so Kai's more or less got it. Zhao Wang is close to some extent. So yes, we've got some good ideas here. So the first thing is that we need these 2 sets to actually be disjoint. And we also need the sum of these guys, i.e. the union of these guys, we need this to be equal to R. Now, there's an interesting point that Zhao Wang made, and this is this equivalent to R1 being equal to the complement of R2? And the answer to that really depends on what you mean by complement. Because when you say take the complement of a set, you mean take everything that's not in that set. But whether or not what that actually means depends on what the overall space is. If we were just looking at taking complements inside of R2 in general, then R2 complement would be everything in R2 that's not in R1. Whereas if we take the complement in R itself, well, we get this back and everything works out. So I think this is a slightly more correct and at least more clear way of defining a partition. So the good thing about working in R2 is that we can actually draw what's going on here. If this is R in total, then a partition just means I'm able to break my setup like that, and there's no overlap. And if I want to find the volume integral over all of this, I just need to do the integral of this plus the integral of that. And the last property that's useful to keep in mind is that if your surface is bigger than another surface, then the associated volume beneath the bigger surface is going to be bigger than the volume underneath the smaller surface. So this is a good thing to keep in mind. All right. Now that we've defined integrals, volume integrals, and we've looked at some of their properties, I wanted to briefly pause to see if anyone had any questions they wanted to bring up or comments they wanted to put forward. I'll leave maybe half a minute for that. All right, let's keep going. Usually, once I've given you a definition of something and I've defined some of its properties for you, the next thing to do would be to do some examples. But in this case, we're not going to do examples, at least not yet, just because this definition is pretty hard to work with. You might remember that when we were dealing with single variable integrals, we only really went into examples once I had given you the fundamental theorem of calculus for single variable integrals. There's not really, there are some analogs of the fundamental theorem of calculus for multivariable integrals, but they're a bit difficult to work with, and they aren't always useful. And so that means that before we do examples, I need to somehow give you another way to actually evaluate these integrals. The way that volume integrals are typically worked out by hand is with the idea of iterated integrals. So if you're dealing with a computer, basically the way you would typically evaluate an integral is via approximations along the lines of what we've just seen, approximate different sub-volumes and add them all up. But if you're trying to work out volume integrals by hand, the idea of iterated integrals is really basically the only way you can really do it. And so let's talk about what iterated integrals actually mean. All right, so the context is this. For simplicity, we're just going to assume that our region of interest is a rectangle for the moment. So just to be absolutely clear about what I mean by this, I mean, I'm looking at a rectangle with x coordinates lying between A and B and y coordinates lying between C and D. If I've got a function and I want to integrate this function over the rectangle R, you can see I'm already being inconsistent with my notation in the sense that I just told you before that we should really have a double integral there. Sorry. Technically, we should have a double integral there. How do we actually evaluate this double integral? Well, it turns out that you can actually do this double integral with two single variable integrals. So that's really nice. So what do I mean by that? Well, it turns out that evaluating this integral can be achieved with a two-step process. The first of these steps is to take your function and integrate it with respect to y from c up to d. Now, let's spend a bit of time thinking about this, what this actually means, because we haven't really done examples like this before, but it's nothing too challenging. The idea is that we just pretend that x is just some parameter. We basically just ignore the facts that our function depends on x, and we just do the usual definite integral of y between c and d. Now, once we do that, we've essentially eliminated dependence on y, because when we do this, we find an antiderivative for f, evaluate it for y equals d, and evaluate it for y equals c, and so there's no more y dependence anymore. However, there is still x dependence, and that gets dealt with by integrating again. So we integrate this x-dependent function with respect to x from a up to b. Now, it turns out that if your function is sufficiently well behaved, continuous functions are an example of functions that are sufficiently well behaved in this context, then it doesn't actually matter which order you do this integral in. You can integrate with respect to y and then with respect to x, or you can integrate with respect to x and then integrate with respect to y. Now, the question you might have is, why are you allowed to do this? The reason for that is it basically as follows, that anytime you're trying to find the volume of a really simple shape, like a cylinder, say, you can do that by finding the area of the circle base and then multiplying that by the height. And in that process, you're basically doing two integrals. You're first doing the area of the base, which is one integral, and then you're multiplying that by the height, which is another integral, because that multiplying by the height is basically adding up all of the individual area components. So in terms of pictures, what's sort of going on here is that if you've got this rectangle here, if you're integrating with respect to y first, then what you're doing is finding the area underneath all of these different curves. So you're going to have to think multidimensionally for this, because there is actually an extra dimension popping out of the page here. So you find the area underneath all of these different curves. We know what that means. But once we have all of these different areas, we should be able to integrate those to get the volume. And this is roughly speaking how it goes. I can appreciate that my pictures aren't as great as you might want them to be to get such a point across, but I hope that does make sense in either case. All right, now that we've got this idea of iterated integrals, we are now finally in a position to actually do an example. And the example is this. Evaluate this integral here, the integral from 0 up to 2, the integral from 1 up to 3, x squared y dy dx. From our previous discussion, we know that this is the same as the integral of x squared y dA, or with respect to the integral of x squared y dA integrated over this region R, which is as follows. So x is going from 0 up to 2, and y is going from 1 up to 3. So we've got a function x squared y. I want to find the volume underneath that surface above that particular rectangle there. All right. Well, using our iterated integrals approach, the first thing we need to do is work out this inside integral here. So the integral from 1 up to 3 of x squared y dy. So what does this mean? We basically just pretend at this point that x is a fixed arbitrary value, and we integrate with respect to y. Well, the antiderivative of y is y squared on 2. So let me just try and explain that. antiderivative with respect to y. So if y integrates to y squared on 2, then x squared times y integrates to x squared y squared on 2. But remember, the fundamental theorem of calculus tells us that we need to evaluate this guy between the numbers y equals 3 and y equals 1. Now, y squared, if y is 3, that becomes 9 squared, x squared on 2, minus x squared, y squared on 2 when y is equal to 1. So that's just 1 squared. Oh, sorry. Just, just 9 there divided by 2. That ends up being x squared times 8 on 2, which is, of course, just 4x squared. So we've now done the inner integral, but now we need to do the outside integral. How does that go down? Well, the outside integral is this guy here. That's the outside integral, and we're trying to integrate 4x squared dx from 0 up to 2. That is actually just that's just a single variable integral that we've spent a lot of time working on so far. And the way to do that is to find an antiderivative for 4x squared. An antiderivative is 4x cubed on 3. And we have to evaluate that between x equals 2 and x equals 0. And, oh, sorry. And that gives us 32 divided by 3. So that's an actual number. As we would expect, we're looking at the volume of a concrete specific rectangle, and that's 32 divided by 3. Now, in the workbook, sorry, not the workbook, the course reader, in the course reader, you'll also find this particular computation as well, where you do it the other way around. So there's another computation you can do, which I'm not going to do because, well, I think this is a good exercise for you guys to try yourself, or else you just look at it in the workbook. Yeah, if you do the integral the other way around, what you'll find is that you get the exact same answer as you expect. When you're trying to find the volume underneath a surface, it shouldn't really matter whether you choose to integrate with respect to x or y first. Okay, are there any questions for this particular example? I'll just have another brief pause. So this was just an example of a function that you needed to find a volume integral of, and it was simple enough for us to be able to do explicitly, so that's great. Now, one of the things that really helped us in this computation was the fact that we were integrating over a rectangle. It seems, in principle, it seems quite easy to integrate over a rectangle, so the question is, how would you use this procedure to integrate things that weren't defined over rectangular domains? There is a rather sneaky way of doing that. So let's consider the following. Suppose we have a function f to integrate over a non-rectangular domain D. Then how would you do that? Well, it's sort of a cheating way of doing it. You simply just redefine the function so that it is defined over a rectangle, and you integrate that instead. So what you do is you consider this new function, which is the same as your old function if you're in the domain of interest. And what happens if it's not? Well, if you've got your domain D and you're trying to integrate the function over that, you just put your domain D inside a larger rectangle and define the function to be 0 outside of that inside domain. Because, well, you may be able to convince yourselves that if you integrate the function f over this domain and integrate another function, which is the same as that over this domain, but is 0 everywhere else, well, that should give you the same answer. And this is one sort of cheating way of getting around it. I have to confess, like I've never seen this sort of technique used. I've never seen this used in a way where other methods have failed. So I guess this is a cute way of defining it over a rectangular domain, but in principle, I don't actually think it makes your life that much easier by doing this. All right, now we're going to get to some more examples of functions to integrate over certain domains. But before we do that, we need some more theory. So the thing is, we're going to try and integrate using polar coordinates. So what does that mean? In principle, if you integrate, whether or not you integrate in polar coordinates or not, it shouldn't actually affect your answer. It's just that in the case that your function as well as your domain, if they both have some sort of rotational symmetry, then it's much more convenient to perform the integral using polar coordinates. So for example, if your domain happened to be a circle, then there is a chance that the integral might be best performed by first switching to polar coordinates. Now, there are some subtleties associated with this, which we'll now go through. So these are just things we need to address before we just charge in and do integrals using polar coordinates. Okay, so what happens here? Well, let's say you've got a function defined on this domain here, and you're trying to integrate it. Now, in principle, you should be able to get the answer just by breaking up into sort of rectangular sort of pieces like before and finding individual volume contributions that way. But in general, if you've got rotational symmetry, you really should be using it. And in fact, in some cases, you have to use it. So we've got some rotational symmetry. And the question is that, well, that means that we really should be using this sort of approximation instead of the silly just mesh grid thing we had before. So we really should be using this sort of discretization of our space in order to perform the integral. But the question really is, what is the area of each of these small rectangles? And this is an important point that we actually need to focus a bit on. The thing is that if we pick this point P here, say, let's say it's at the coordinate r star and theta star. So r star means how far away it is from the origin, and theta star, I guess, is how much rotation it's had from the x-axis. Then the area of this particular rectangle is approximately r star times the change in r. So this would be change in r, and this would be change in theta here. Now, this might come as a bit of a surprise to you, because when we think about rectangles like this, we know that the area is change in x times change in y. So we've got a bit of a question which I would like you to put an answer to if you have, because I want to spend some time talking about this. Why do we need that r star there? Now, you may think the answer is obvious, and if you think it is obvious, please do write it down in the chat. But even though some of you may think that this is obvious, it is actually a really, really important point, because students quite often forget about this. So I'll invite you to give me your thoughts about why we need this factor r star here, and why is it not just delta r times delta theta? Why do we need this r star in front here? So I've got a comment here saying exchange rate. I'm not exactly sure what you mean by that. Perhaps you could elaborate, but we've got another pretty good answer here from Zhao Wang. The closer you get to the origin, the smaller the area is, and that's precisely right. Now the question is, why is it r star instead of something like r star squared or something else? So this is something I might just answer myself. So let's think about this. What we've got here, let's say that we've got some sort of quarter circle thing here. Actually, no, quarter circle. Let's do an eighth of a circle just to really make this a bit more obvious. Okay, now let's say we've got an eighth of a circle. And let's say here we've got r equals 1. Let's say here we've got r equals 2. And here we've got r equals 3. Now, since we're dealing with an eighth of a circle, that means that the change in angle here is going to be 2 pi divided by 8, which is pi on 4. Now, how are we going to estimate? Didn't really do it very well proportionally. Let's do that. What we're going to do is try and work out the areas in each of these regions using the formula for the area of a rectangle. Because the idea here is that we can, at least if we're far enough away, we could think about this as in terms of, base times height. What is the height? Well, the height is the change in radius, which is just 2. Sorry, no, it's just 1. The height equals 1. Now the question is, what is the base height? What is the length of this line here? Approximately. So basically the only, what we're going to use is the fact that the perimeter of a circle is 2 pi times the radius of that circle. So if we're looking at radius equals 2, then the perimeter of the whole circle is 4 pi. And so the length of this particular section is about pi on 2. And you may notice that this is twice pi on 4. And that's not a coincidence because we're looking at the r equals 2 level. On the other hand, the length of this section is pi divided by 4. That's because the length of a circle of radius 1 is 2 pi, and 2 pi divided by 8 is pi 4. So it's really important to notice that, the further away we go, the bigger the length of these rectangles get, and that's because we're at a bigger and bigger radius. And so I hope that gave you some sort of a convincing that we do actually need this r star here. So in principle, what that means is that if we're integrating this function using polar coordinates by adding up volume contributions of each of these, what we've got to do is work out what the value of the function is at some candidate point inside that subregion. We've got to multiply by the radius that we're at, and then multiply by the change in radius and the change in angle of that particular annular patch. Okay, so in principle, what that means is that if you want to do a volume integral in polar coordinates, you need to do this. So if you've got a function f of xy, you need to write, well, x is the same as r cosine theta, and y is the same as r sine theta. And in principle, you can do that by integrating over the domain D. D is the set of all r and theta, so that r is less than something and theta is less than something. But the important thing here is that you need to include this r. So this is very important. Don't forget about this r. This r is called, in some, you may have seen this before, r is called the Jacobian of this change of variables. Okay, we're now going to have a look at an example of this. We're going to now do an example that uses these particular volume integrals. And the example we're going to do is a very, very important one. The integral of e to the minus x squared minus y squared dx dy, where d is the region bounded by the circle x squared plus y squared equals r squared. So in polar coordinates, this is a set of all angles and radiuses, radii, so that 0 is between small r is between 0 and capital R. And theta, well, it's a circle. There are no constraints on theta. Theta just lies between 0 and 2 pi. So this is our domain. Of course, we all know what this thing would look like. It's just, we've got a function and we're trying to integrate it over this particular region here. So that's what this region looks like. Now the question is, how do we do this? How do we actually do this integral? Well, since we've got lots of good circular symmetry here, what we're going to do is use polar coordinates. In polar coordinates, we can do this as an iterated integral. If we do it as an iterated integral, that just means we have to integrate with respect to one variable and then with respect to the other variable. Now, the thing is, if x is equal to r cosine theta and y is equal to r sine theta, then x squared plus y squared is equal to r squared of cosine squared plus sine squared of theta. And this is just equal to r squared, because cosine squared plus sine squared is always equal to 1 if you're looking at the same angle. And so that means that this e to the minus x squared minus y squared just becomes e to the minus r squared. Now, it turns out that for this particular example, it's nice to do the r integral first, although it doesn't really matter. 0r e to the minus r squared times r dr. So this is the inner integral that we have to do. So since we're integrating with respect to r first, the bounds of this integral are going to be 0 up to r. And since we integrate with respect to theta last, theta goes there. Now, because if we evaluate this inside integral, there's actually a step missing here. I wondered if you could tell me what particular choice of single variable integral technique did I actually use to do this integral? So there's not too many that we did. I wondered if you could just put a message in the chat indicating what integral technique I used to do this. Yes, this was an integral by substitution. And so if we're just focusing on this particular integral here, the integral from 0 up to r of 0 minus r squared r dr, I'm going to let u be equal to r squared. So that's du equals 2dr, so that this integral becomes the same as the integral from 0 up to the square root. Wait. If r is going to capital R, okay, so this would be actually equal to r squared of e to the minus u r dr. Oh, sorry, I missed an r here. Well, we know that this is actually equal to half du. And that's something I actually know how to integrate. And so that's how I would get this particular line here. And then the 2 pi just comes from the fact that I'm integrating from 0 to 2. Oh, sorry, typo here. This should be 2 pi. So the 2 pi comes down there. This isn't just an evaluation I know how to do. And what I end up with is pi outside of 1 minus e to the power of minus r squared. So this is how you perform an integral using polar coordinates. Now, what becomes really interesting is if you do this integral over not just the circle, but over the entirety of the set of, well, over the entirety of R2. So evaluate e to the minus x squared minus y squared dx dy over the entirety of R2. Well, as we just saw, it's easiest to do this using polar coordinates, except this time it's the exact same computation before, except this time we're going all the way to plus infinity. Now, I haven't really explained what I mean by plus infinity yet, but it basically just means take limits, of course. What I end up with using this exact same computation, I get the answer pi. Now, this is a very, very phenomenal result and somewhat surprising, I would say, because, well, in some sense, that this gives us a link between 2 of the most interesting irrational numbers we know of. Pi is a very fundamental irrational number, and e is another very fundamental irrational number. And if we perform this very interesting integral, it turns out we get a link between the 2 of them. Now, it is important that you remember this, because this sort of computation is one that you will actually do in your assignment. I can't remember which question it is, but you're asked to prove that the integral of e to the minus x squared from minus infinity to infinity, you're asked to show that this is just equal to the square root of pi. How might you do that? Well, I mean, if you happen to have access to this particular computation here, you might be able to use the facts that, well, using what we know about double integrals, this guy here is the same as the integral from minus infinity up to infinity, and then another one, not really choosing good colors here. The integral from minus infinity up to infinity, integral from minus infinity up to infinity of e to the minus x squared minus y squared dx dy. But of course, we're just dealing with single iterated integrals here. We know that e to the minus x squared minus y squared is the same as e to the minus x squared times e to the minus y squared. So we can actually write that this way. Now this inside integral is just some number. So we can also take it outside. And what we end up with is this. So that particular computation there is actually a result that'll help you show that this is true. So some of the details that I haven't covered in this, you'll need to fill out in your assignment, I expect. All right. So there's just one last thing I want us to do before we break, and that's explain rigorously what I actually mean by this infinity here. This is an example of an improper integral. So improper integrals just mean you're doing an integral that involves infinity in some sense. You're integrating something over an unbounded domain. So, and I haven't actually defined that for you yet, but we'll fix that problem right now. Let's suppose that you've got a single variable integral now, so that if you integrate from a up to t, then this always exists whenever t is bigger than a. Then the question is, what do we mean by the integral of f of x dx from a up to infinity? Well, that means we take this integral from a up to t and simply take the limit as t goes to infinity. Because if we take t to infinity, we know we're getting all of the area that we need to include. Of course, the exact same thing happens in reverse if we want to put the minus infinity on the subscript. So this is the same as the integral from, let me just swap these around, it looks like. The integral from t up to b f of x dx, and we send t to minus infinity. So, of course, it may be the case that these integrals don't always exist because the limit doesn't exist. But if these limits do exist, then we say that these integrals are convergent and they're going to be divergent otherwise. And the last thing we'll do in this integral chapter is explain what it means to integrate from minus infinity to plus infinity, because that's an integral I just included without really describing to you its definition. And the definition is as follows. If, no matter what a you pick, these integrals exist, so these integrals taken with respect to the definition just given, then we can define this integral from minus infinity up to infinity to be the sum of these two particular integrals. And the important thing to note is that this definition doesn't actually depend on a, as long as these two integrals are both convergent. As long as these two integrals are both convergent and f is sufficiently well behaved, then this answer here doesn't actually depend on your choice of a. So this actually concludes our chapter on integration theory. This concludes Unit 9. So now it's probably a good time to have a 10-minute break. It's now 5:53 p.m. and we'll reconvene in 10 minutes. Since this is the end of a chapter, please feel free to include questions you may have about the contents or requests for clarifications on anything, and I'll endeavor to answer your questions. I'll see you in about 10 minutes. Hello again, everyone. Doesn't seem like there were any additional questions in the chat. So I'll assume that everyone is happy with integration, and we'll now move on to the last unit in this course. And this unit concerns multivariable functions. Specifically, we'll be talking about partial derivatives of multivariable functions, and we'll be talking about gradient descent. Now, gradient descent is something that does come up a lot in artificial intelligence and machine learning, because, well, as I may have mentioned on a number of occasions, that machine learning and artificial intelligence mostly boils down to, or maybe that's a bit of an overstatement, it boils down substantially to an optimization problem. And understanding the theory of partial derivatives and gradient descent is important to do that, because the functions you're optimizing in machine learning and artificial intelligence are not single variable functions. They are very, very multi-valued functions. And so you need to understand the language of mathematicians for partial derivatives, specifically partial derivatives and gradient descent, in order to, in my estimation, make good progress towards those data science topics. So, let's get started with some partial derivatives. So, section 10.1. Section 10.1, partial derivatives and tangent planes. So let's suppose that we've got a function of two variables. Of course, in real life, you're going to have to deal with functions of many more than two variables, but for the purposes of simplicity, let's say we've got a function of two variables, and let's just choose any old point, x0, y0. Now, what we're going to be looking at is tangents, planes, and slopes. So we know that if we're talking about single variable derivatives, the derivative is basically a measure of how steep the tangent slope is at a particular point, whereas in multiple dimensions, what we start talking about is tangent planes instead. But nevertheless, the single variable theory still gives us a lot of good information. And so the single variable theory becomes useful if we fix one of the variables and just look at traveling in the direction of the other variable. So we would then say that the slope of f at p in the x direction is found by taking the partial derivative of f with respect to x. So what this means is basically you just take, you imagine that y0 is now fixed, and so you've now just got a function of x, and you do your usual derivative of x. You find the slope of that function at the point x0, and that's going to tell you the slope of the overall function in the direction of x at that particular point p. Of course, you can do the exact same thing in the y direction. So it's handy, I think, to go through an example of what this actually means, and hopefully we can visualize what this actually means. So for the sake of argument, let's just suppose we're dealing with a function f of xy equals 1 minus x squared minus y squared. And let's suppose that we're dealing with the point 1, minus 1. So x0 is 1 and y0 is minus 1. We're interested in taking partial derivatives. So to do that at the point 1 minus 1, well, to take the derivative in x, we fix y0 at minus 1. Why would we do that? Because the function we just end up with is minus x squared, and so taking the derivative is easy enough. The derivative is equal to minus to x, but we've got to evaluate at the point x equals 1. And so that brings us to the number -2. You can do the exact same thing in the y direction, because at the point 1 minus 1, f of 1y is just minus squared. I think that's another typo there. And so that means if you take the derivative, you're going to end up with -2y, but you're evaluating at the point y is equal to -1, so that gives you the number 2. So here we've got some graphical representations of what's actually going on here. So this yellow surface is precisely the function f of xy equals 1 minus x squared minus y squared. And this line here is telling us what happens if we fix y naught at, I can't remember which way around each is, but one of these is found by fixing y and changing x, and the other is found by fixing x and changing y. And being able to do this gives us single variable functions, which we can differentiate to find the slope. So this is all great. So what can we do with this? Well, just in an attempt to solidify this theory somewhat, I'm going to go through an example, a rather geometric and physical example. If you've got a solid, a three-dimensional solid, a rectangular prism to be precise, and its side lengths are x, y, and z, then the volume we know is found by multiplying these three numbers together, x times y times z. The question is, calculate the partial derivatives of v with respect to all three of these variables. So you can see we've actually jumped from 2 variables to 3 variables now, but of course the theory still remains the same. The derivative in x is found by just imagining that y and z are constants and differentiating with respect to x. Since yz is a constant, that just comes out the front, and the derivative of x is just 1. So in laborious terms, this is that computation there. Of course, you can see that almost the exact same thing occurs for all of the other partial derivatives. If we differentiate with respect to y, we'll just get xz, because xz goes out the front, whereas the y gets turned into a 1 when you differentiate it. And a similar thing happens for the derivative with respect to z as well. Okay. So these are the first derivatives. What about, can we go higher than that? Yes, we can. Just in the single variable case, we can take first derivatives and second derivatives. But what's interesting about the multivariable case is that you can start having mixed derivatives. So you can have derivatives where you differentiate with respect to one variable and then differentiate with respect to the other variable. So let's just go back to 2 variables for the moment. The second order partial derivatives, you find these by differentiating once with respect to one of your variables, and then you differentiate again with respect to another variable. And the important thing is that these 2 variables do not need to be the same. So let's introduce notation. Since we'll be differentiating with respect to lots of different variables, it'll be good to make sure we've solidified the appropriate notation. And there's essentially two different notations that we can use. The first is where you literally just write a subscript listing all of the variables that you're differentiating with respect to. So this one you differentiate with respect to x, and then you differentiate with respect to x again. Another typo, this is f of yx. This one here, you differentiate with respect to x first, and then you differentiate with respect to y. This one, you differentiate with respect to y first, and then differentiate with respect to x. You can also do this using this sort of partial notation here. All right, so if you've got a function of two variables, then these are the four different partial derivatives that you can possibly come up with. Now, question: let f of xy equal x times sine of y plus y times cosine of x. Calculate all of the second order partial derivatives and show that f of xy is equal to the same as f of yx. So what this is asking you to do is to show that these two things are actually the same. It doesn't matter whether you differentiate with respect to y first, or if you differentiate with respect to x first, you're going to get the same result. And even though I haven't included this computation in the slides, I suppose we may as well do it. So first things first, the derivative with respect to x. Well, the derivative with respect to x is just sine of y, because sine of y is just a constant for the purposes of this computation, and x differentiates to 1. On the other hand, the derivative of cosine x is minus sine of x, and the y goes out the front again. If we differentiate with respect to y, well, the x goes out the front, and the derivative of sine of y is just cosine of y. And if we differentiate again, the derivative of y is just 1, and the cosine x comes out the front. Okay, but it's asking us to find the derivative of f with respect to x, and then differentiate that with respect to y, and then do the same thing in reverse. Well, if we differentiate this with respect to y, what do we get? Well, we have to differentiate this with respect to y. The derivative of sine y is just cosine y. The derivative of y is just 1 sine of x. On the other hand, the derivative of f with respect to y with respect to x, this is equal to cosine y, because cosine y just comes out the front, and the derivative of x is just 1. And then we've got to differentiate cosine of x, but that just gives us minus sine of x. So this is nice. These two things happen to be the same thing. This is not a coincidence. It turns out that the fact that it doesn't matter which order you differentiate things, it's always true if f is sufficiently well behaved. I imagine you might be getting sick of me saying the term sufficiently well behaved without providing more context. There is more context, but most of the functions, unless we specifically design a function to trick you, most of the functions that you'll come across in this course will be sufficiently well behaved. So, for example, this is true for all polynomials. All right. Now we're getting interested in the theory of combining the observations of the partial derivatives to give us new information and better insights about how a function behaves. So, for example, you may remember that if we've got a function of multiple variables, then, and it so happens that we take a point and we move x a little bit and we move y a little bit, then the total amount that f changes by is the same as the total amount that x changes by multiplied by the derivative of f with respect to x. And then we multiply by the amount by which y changes with the derivative of f with respect to y at that particular point. So in principle, what this means is that if x and y are both dependent on another variable, time, for example, and we know how quickly x and y are changing with respect to time, we can change how much f is changing over time. So this brings us to a chain rule of sorts, because we've got a function f which depends on things which depend on something else, whenever that happens, we start thinking of the chain rule. And in particular, what we've got here is the multivariable chain rule. Now, this does get a bit complicated, so I'm happy to spend a bit of time thinking about this. If you've got x and y being functions of time, and it so happens that f is a function of x and y, and I want to know how quickly f is changing with respect to time, I can do that. I can do that with the multivariable chain rule. And the way I do that is, roughly speaking, just by dividing through by delta t and taking limits. And what I end up with is that the derivative of f with respect to t, because if x and y are functions of t, then you can think of f as a function of t and nothing else. And this is the same as the derivative of f with respect to the x coordinate multiplied by the amount that the amount that x is changing by. And then you've got to multiply by the derivative of f with respect to y times dy on dt. Now, we've got a good question here. Is there a proof of this particular rule? It depends on what you mean by proof. Unfortunately, the actual proof, the correct proof of this result is very tricky, because in order to do the actual proof, you need to use the fundamental definition of limits, which involves epsilons and deltas, and that's a particularly challenging thing to do. On the other hand, if all you're really looking for is a simple proof, let's think. I suspect I won't be able to come up with something great off the top of my head. So any proof I come up with that's intuitive is basically just going to be a consequence of this. So I'll talk to you, Casey, directly for a bit. Are you happy with this particular approximation here? Yeah, so I mean, basically what this is saying, this is basically just the equation of the tangent plane. So if you've got some multivariable function, so the idea is that let's just say I've got a multivariable function here, and I've got this as my tangent plane. Now, I guess the important thing about the tangent plane is that for the purposes of taking a single derivative, the tangent plane actually contains all of the information. So for example, let's say that my tangent plane is f of x, y. Let's just say, okay, for the purposes of simplicity, let's say that I'm just taking my derivatives about 0. I think that's a fair enough assumption to make. Now, let's say that the tangent plane of this function is equal to ax plus by. Now, of course, this is actually just an approximation, so technically speaking, I shouldn't be saying it's equal to. F of xy is approximately equal to some number a times x plus b times y. And we know that a is the derivative of f with respect to x, and b is the derivative of f with respect to y. Now, there are other terms here, but all of these other terms don't have a contribution when it comes to derivatives. So the other terms don't count towards derivatives. If all of a sudden now you actually just say, well, actually, I've decided that my x and y functions actually depend on time as well. So x depends on time and y depends on time. Then I think it's pretty clear from this that if you differentiate this with respect to t, you're just going to get a times the derivative of x plus b times the derivative of y. So I think that's probably about as extensive as I can get to you. Yeah, so I'd say the result is pretty clear if you're just looking at planes. If you're just looking at like multivariable functions that are just planes, in that sense, that the result is pretty obvious, and the fact that the result is true more generally is a consequence of the fact that locally any function looks like a plane plus some other terms that don't actually have any meaningful contributions to the derivative at that particular point. So I hope that all makes sense. But yeah, it's basically just a consequence of this particular fact there. So yes, I'll just read your question out just in case people are a bit unclear. So you're suggesting that your understanding of the top equation, I presume that's this one, the top equation is that the change of f is the combination of changes on x and y components respectively. Is it the right way to understand this? And is it more a vector with direction? Okay, so we're actually going to get to using vectors to describe all this shortly. At the moment, there are no vectors here. I'm just multiplying numbers. These are all just real numbers at this stage. But yeah, that's precisely the way to think about it. If you change x by a small amount, the amount that f changes by is going to be determined by how much you're changing x by, as well as how steep the slope of f is in the direction of x. On the other hand, the same is true for y. If you change a y by a little amount, then the amount that f changes by is going to be the amount that y changes by, as well as multiplied by the steepness of the slope of f in the y direction. And if for whatever reason you decide to do those two things at once, well, you just basically sum the contributions to work out what the total net effect on the change of f is. So we'll now get into an example. Oh, okay, another question, but x and y have directions and are orthogonal to each other. So the sum is a vector with direction. No, because at this point, this component here, the change in x, that's not a vector. That's just some number that describes how much I'm changing x by. I don't actually need to talk about directions just yet. I'm hoping that as we get into vector stuff shortly, this will become a bit clearer. But I think that's mostly stuff we'll do in, we'll get onto the vectors, the vector approach to this sort of talk in chapter 10.2. So maybe you can wait till we get there and you can tell me if you're still having trouble understanding this, and we'll see what we can do. Okay. Another question. Would we also deal with the algebra part of vectors? I don't know exactly what you mean by, space and subspaces. No, we're not dealing with vector spaces and vector subspaces in this course. That's, if you want to do that stuff, you really need to take a linear algebra course. I'm not sure if that's something you would actually do as part of the Masters of Data Science, but I'm sure that any number of the textbooks that are listed in the electronic course profile would help you understand those ideas. Alrighty. Thanks for your question, guys. It's good to have these contributions. We'll now get into a question which might explain the utility of the multivariable chain rule. So the context is as follows. We've got a cylinder, but for whatever reason, the dimensions of the cylinder are changing. We've got a radius, which is changing at 2 centimeters per second, and we've got a height, which, even though we say it's a function, it is actually just a constant. The height is kept constant at 2 centimeters. How fast is the volume decreasing when the rate of change, how fast is the volume decreasing when the radius is precisely 1 centimeter? Well, we need a function which relates the volume to the height and the radius, but of course we know that the formula for the volume of the cylinder is just the area of the circle pi r squared times h. So with the multivariable chain rule, we find that the derivative of v with respect to t is the same as, let me just remind you what the formula is. dv on dt equals the derivative of v with respect to r times dr on dt plus the derivative of v with respect to h times dh on dt. Now, the derivative of v with respect to r is precisely 2 pi r times h, because r squared differentiates to 2r, and dr on dt is just r prime. On the other hand, if I differentiate the volume with respect to h, I get just pi r squared, because h goes to 1, and so I end up with this term here. Now, the thing is that the height is actually kept constant. So in this sense, this is a silly example of the multivariable chain rule because, well, one of the variables is constant, so it's basically just the regular chain rule. But in any case, h prime vanishes, so we're just left with this term here. But I now know what all of these things are. I know that r is 1 centimeter, I know that h is 2 centimeters, and I know that r prime is minus 2 centimeters per second. So keeping appropriate track of the units, I end up with minus 8 pi centimeters cubed per second. And that's good because that's precisely the unit we would expect, given how we're dealing with how quickly the volume is changing. So as I said, that was a bit of a silly example of the use of the multivariable chain rule. So let's have a look at an actual, a true use of the multivariable chain rule. Let's suppose that in addition to the radius changing at 2 centimeters per second, let's say that the height is now also changing at 1 centimeter per second. What is the change of volume? Well, the good news is that this same computation is still true. So the same computation as before, except now what happens? Well, r is again 1, h is still 2, r prime is again 2, r squared, well, 1 squared, h prime, that's 1 centimeters per second. And this time we see, as we would expect, that the volume is changing more quickly than it was last time because height is decreasing. Now we've got minus 9 pi centimeters cubed per second. Okay, so this is an example of the chain rule for 2 variables. Now, I think the last thing we're going to do in section 10.1 is talk about an application of the use of the chain rule for 3 variables. All right. So let's suppose now we've just got a box. Let's say the dimensions of this box are A, B, and C. So height, width, and length, or any permutation of those. Finds the rate of change of the volume of the box. Well, the volume we know is A times B times C. So the derivative of v with respect to t is the derivative of v with respect to a. So just remember, you can use different ways of using different notations I can use here. dv on dA times dA on dt, dv on dB times dB on dt, and then the same thing for c. Now the thing is, I know what all of these partial derivatives are. The derivative of v with respect to a is just bc. The derivative of v with respect to b is just ac. And the derivative of v with respect to c is just ab. So this is the formula. We haven't been given any numbers or anything else in the question, so this is actually the best that we can do. So that's how we would use the chain rule for 3 variables. All right. Now, section 10.2, we're getting into discussing the gradient. This is where we start talking about vectors. All right. Now, as I said before, we've got, for a function of 2 variables, we've got 2 numbers. At a particular point, we've got 2 numbers, the derivative of f with respect to x and the derivative of f with respect to y, which tell us the slope in these 2 particular directions, x and y. However, it turns out that by combining these 2 things into a vector, you can basically use a combination of these 2 real numbers to get the slope of the function traveling in any direction. And the reason we can do this is precisely because of the chain rule. So let's be a bit more specific about this. Let's say we've got a point P and we want to travel away from P in the direction of u. So u, consisting of components u1 and u2, is just some vector, and I'm going to assume it's a unit vector just for simplicity. So just before I keep going, I've got another good question. This question is about whether or not we're going to deal with surface, line, and volume integrals. Unfortunately, the answer is no. In this course, we won't be dealing with line integrals. Yes, unfortunately, as you point out, being able to do these sorts of integrals being able to do these integrals is quite important, especially if you're studying physics. But I guess we've decided that it's not entirely what we're going to be doing in this course. You may have noticed that we've been trying to cram a lot of stuff into this course, and including surface and line integrals might be pushing it a bit too far. But if you're interested, I think that, well, I learned this sort of stuff from the Advanced Engineering Mathematics textbook by Kreutzig, if you'd have a look at that. But I'm sure many other physics textbooks would have such information. All right, back to our gradients. So recall we're looking at a point P in the plane, and we're traveling away from P in a particular direction, and we're going to use the vector xt, yt to keep track of this information. So just to be absolutely clear about what's going on here, x of t is a scalar, y of t is a scalar, but the vector, where you chuck these 2 things in as components, this is a vector. So this may help you notation-wise as we're going through this. All right, now the question is, what is the slope of the function in this particular direction? Because now I can, since x and y are just depending on t, that means I can think of f as a function of t, and I want to know how quickly f is changing with respect to t, because that will tell me the slope. How do I do that? Well, lucky us, we just did the chain rule, and that's precisely what we need to do this computation. So remember, using our tangent plane approximation here, the change of f is going to be the same as the derivative of f with respect to x multiplied by how much x is changing by. X is changing by u1 times t. Y is changing by u2 times t, and then I get a derivative of f with respect to y at the front. But of course, this is precisely equal to f evaluated at p plus the dot product of two vectors. The first of the, well, t comes out the front. The first of these two vectors is the vector whose first component is the derivative of f with respect to x and the derivative of f with respect to y. And we're taking the dot product with u, where u is this same vector from up here. I expect you may have covered dot products in an earlier unit, but just in case you're unaware, by definition, the dot product of two vectors is just found by cross multiplying and adding up. So add up those and add up those, and this is a scalar. So I'm basically now in a position to find the slope. The slope is just going to be this. Everything here except for the t. So this guy here is therefore going to be the directional derivative of f at the point P in the direction of u. And you can also think of this as the slope, because if you go f of t minus f of 0, this is approximately equal to t, and then divide by t, this is approximately equal to this vector here, dot producted with u. So this is the directional derivative. Okay, so we've got a question here from KC about it's a technical question about the actual use of the dot product. Don't we have a cosine theta in the dot product if they are not in direct line with one another? Now, you're talking about another way to calculate the dot product that is actually the same. So let me try and explain what's going on here. It's been a while since I used that particular formula for the dot product. Do I have space somewhere else? I'll just use this as blank space to explain the dot product for you. So the dot product is what happens if you have two vectors and you somehow want to combine them to give a scalar. So I think you just answered your own question there. So if you've got two vectors, A1 and A2, and you want to take the dot product, I think the classical definition is A1 B1 plus A2 B2, but there is another way of doing that, and this is found by doing this. So I think this answers your question because, of course, this is exactly equal to the absolute value of A, and this is equal to the absolute value of B. So the fact that this is true is, I consider the fact that this to be true a bit difficult to convince you of right now, but there are two. Yeah, there are two different ways of defining defining the dot product. Now, I might blow your mind a bit with this one, but I'm now going to ask you a question because I'm interested to have this conversation with you. If I give you two vectors arbitrary vectors, how do you define the angle between the two of them? So I think I've got you. and my answer to the question, how do you define the angle between two vectors, is precisely with this formula. Because if you define the dot product of two vectors to be this, then you can define the angle between the two of them to be the unique angle, so that the cosine of this is equal to this divided by this. So in the absence of obvious geometry, I think that the correct way to define the angle between two vectors is precisely with this formula. So yes, there we go for that one there. All right, back to directional derivatives. Oh, sorry, last point on that slide, that technically speaking, this is what we did for unit vectors, but the question is, what happens if U is not a unit vector? Well, you basically just divide by it, so that what you do end up with is a unit vector. So that's the directional derivative in that case. Let's have a look at an example of the use of these directional derivatives. All right, so we've got a function. The function is of two variables, and it's defined to be 4 minus x squared minus 4y squared. We're not just looking at the directional derivative anywhere, we're looking at the directional derivative at the point 1, 1, and we're also going to be looking in the direction of the point 1, 1. So we're evaluating the directional derivative here, and we're going in that particular direction. All right, well, remember, it's convenient to deal with unit vectors here. I'm going in the 1, 1 direction. The actual unit vector that's associated to that is this one here. So in case you're unfamiliar with this notation, I means this vector here, and J is this vector here. So this is the unit vector which describes the direction that we're traveling in. So let's go about computing the slope. Well, to compute the slope, I need the partial derivatives, but this is easy enough to do. The derivative of x squared with respect to x is 2x, and the derivative of y squared with respect to y is 2y, and of course the 4 comes out the front. But this means I now know what the directional derivative is. I just simply have to take the dot product of the vector, which has these as components, with that guy there. So since I'm evaluating at the point 1, 1, this vector becomes minus 2 minus 8, and I'm taking the dot product with 1 on root 2, comma 1 on root 2. Using the definition of dot product that I gave you before, we end up with minus 10 on root 2, and this is equal to minus 5 times the square root of 2. So this is how steep the slope is if we're traveling in the direction of the 1, 1 vector. Okay, let's do another example. This time we're looking at the function x squared minus 3y squared plus 6y. The point at which we're interested in is 1, 0, and the direction we're traveling in is I minus 4j. So just one more time, I is the x direction basically, and j is the y direction. Alrighty. Well, it's just a computation. I have to find the appropriate unit vector. So I minus 4j is not a unit vector. In particular, its norm is root 17, but that's fine because it means I can find a unit vector just by dividing u by root 17. And to do this, to find the slope, I also need to find the derivatives. Well, the derivative of f with respect to x is just 2x. On the other hand, if I differentiate with respect to y, I get minus 6y plus 6. Right, now I need to evaluate this at the point 1, 0. Well, when x is 1, this just becomes 2. And when y is 0, this just becomes 6. And I'm taking the dot product with this vector divided by root 17. Just a computation. I end up with minus 22 divided by root 17. Now, I think the last thing I'll do before we break for another 10 minutes is to give this vector a name. Because remember, this vector is df on dx, df on dy. This vector comes up a lot. In fact, it's already come up 2 or 3 times this class. So it's good to give it a name. And we call it the gradient vector. So if you're given a function of 2 variables, then the gradient of f at a particular point is the vector whose first component is f of x, by which I mean the derivative of f with respect to x. And the second component is the derivative of f with respect to y. The reason this is so important is because it makes describing the slope really easy. Because if you're looking at the slope in the direction of u, well, the slope is found just by taking the dot product of the gradient of f with the unit vector which describes the direction that you're traveling in. So when we're now talking about vectors, yes. So I think I might leave it there for 10 minutes. So we'll stop there and we'll come back in 10 minutes. Again, if you have any questions, if things are still unclear, anything I've said, please let me know and I'll seek to address it when I get back. Hope you have a good break. Oh, fun question. How did the class do overall in quiz 2? Pretty well. I mean, it's a difficult question to ask. Not, the highest mark was 99. There were several people in the high 90s. I didn't give anyone 100% because I managed to find, well, yeah, I did find things that displeased me about all responses. So no one got 100%, but there were several people in the high 90s. Yeah, probably all the information I'd feel comfortable giving out. I'm not sure. Yes, I can't imagine it'd be appropriate to tell you too much more. Maybe you only thinks it's appropriate. I could ask him, I suppose. Yeah, okay. So we'll get. Hope you have a good break. I'll see you around. Hello again. Okay, so we've been making progress towards understanding the gradient, which is useful. It's a useful summary of the information given to us by the derivatives of f with respect to x and the derivatives of f with respect to y. So before we get more into it, we've got another comment. These questions deal with the real number line. Are there any examples that deal with the complex domain? In this course, we're mostly just dealing with real parameters. Now, the reason for that is that you typically, if you wanted to do complex analysis with complex functions, then you really need a good reason to actually be doing stuff in the complex domain. Now, as far as I can tell, in terms of like real life applications of complex numbers, the most obvious one that comes to mind is in electrical engineering, because they find it quite convenient to introduce an additional complex number to keep track of things, because it simplifies a lot of the algebra. For all of the applications we're looking at in this particular course, it turns out that there's no real reason to go to the complex domain. And so while you can do a lot of these things in the complex domain, I guess we've decided to keep it simpler by not going to the complex domain, because we don't have to. Yeah. So yes. So I mean, you know, like to some extent, you can identify R2 with the complex numbers, but there is additional structure that the complex numbers have that we don't really need to focus on in this course. And so for that reason, we just don't bother with C at all and just focus on R2. So yes, that's what I consider to be like the correct answer to your question about why we're not really doing that in this course. All right, so we just defined the gradient vector. We want to, let's just have a look as an example. So let's say we've got the function x squared minus 3 times y minus 1 squared plus 3. Okay, what is the gradient? Well, the gradient is the vector filled up by the partial derivatives. So the derivative of f with respect to x and the derivative of f with respect to y. These are derivatives I hope you're all able to do. df on dx and minus 6 times y minus 1. Now, if you're wanting to do this with the old ij notation, you would do it by this. This just goes there, and this just goes over there. Okay. Now, we're going to look at another example of directional derivative, except this time we're going to do it with the gradient notation that we just introduced. So let's say we've got the function g of xy, which is equal to e to the power of x squared times cosine of y. We're looking at it at this particular point here, and we're hoping to go in this particular direction. All right, first things first, let's normalize. Well, let's at least work out how big this vector is. You may notice that this is a Pythagorean triple, because 3 squared plus 4 squared is the same as 5 squared. So the norm of this vector is 5. It's a good start. And we also need to work out the gradient of this vector. So this is the vector whose components are filled up with the partial derivatives. So the derivative of g with respect to x and the derivative of g with respect to y. It follows our usual differentiation rules for exponential and trigonometric functions. Now that we've got the gradient, we're now in a position to find the directional derivative. The derivative of g in the direction of u is found by evaluating this gradient at the point x equals 1 and y equals pi, and dot producting that with u divided by the norm of u to make sure that our vector is normal, unit vector that is. Well, if we chuck in x equals 1 and y equals pi in this expression here, we end up with this vector here. Take the dot product of this vector, which is -3 divided by 5 and 4 divided by 5. And in the end, we find that the slope is 6e on 5. Okay, now for a bit of geometric intuition. If you've got a function of two variables, the gradient at a given point is a vector. It points in a direction. And it turns out that this is not just any direction, that there is meaning behind the direction that this vector points in. It turns out in general that, well, this almost follows from definition of the gradient, that this gradient always points in the direction perpendicular to the contour passing through the point AB. So if we think about contours are lines where f is constant. So for example, we could have f equals 2 along this line, and we could have f equals 1 along this line. It turns out, this is basically just a consequence of the chain rule, that this gradient is always perpendicular to these tangent lines. In particular, the gradient of f always points perpendicularly outwards from these lines. This is basically just a consequence of the chain rule, as I said. Now, what this means really is that the gradient of f always points in the direction of the sharpest increase of f. So I found a nice illustration of this from Khan Academy. So we've got a particular function here. The function is f of xy equals x times y. And what is happening here is we've got a graph of the contours. So these are lines where the function is constant. Now so those are in blue. So the contours are in blue. On the other hand, the gradient at each point has been evaluated. And remember, the gradient is a direction. And so that's been put in here with purple arrows. So what you may notice is that these purple arrows are always pointing perpendicularly to their contours. And what this means is that this is actually pointing in the steepest direction, in the steepest possible direction to give us the greatest increase of the function f. Now, it's this observation that makes the gradient an important thing to observe when we're dealing with optimization problems. But before we get into that, let's just go through an example to sort of convince you of why this geometry holds true. So let's consider the function f of xy is equal to mx plus ny plus c. M, n, and c are just real numbers. N is a non-zero number. That's important. Finds the gradient, finds the contours. Compare. All right. Well, the contours, remember, these are just lines where f is constant. So if f is just some constant c, well, this is equal to mx plus ny plus c. We end up with mx plus ny equals c for some new constant. I've basically just absorbed the two c's together. And what we end up with is, well, rearranging, we get y is equal to c minus mx divided by n. So that's where we're going up there. The other important thing to note is that the gradient is found with the vector whose first component is just the derivative with respect to x. So that's m. And the second component is the derivative of y. Sorry, is the derivative of f with respect to y, which is just n. Now, the important thing to observe here is that if we take the dot product of the gradient with the slope of this particular line here, what's the slope? Well, the slope of this line, it's just a function y of x, so the slope of this line is just 1 minus m on n, because if x changes by 1, then y changes by minus m on n. This ends up being mn dot product 1 minus m on n, but of course this just ends up being 0. So this is the reason that the gradient is always perpendicular to lines of constant f. So it's basically the same reason as before. This computation shows that it's always true in the case that f is just some plane, but what happens in the more general case that f is not a plane? Well, I mean, at any given point, f can be expressed as some plane plus some terms which become negligible for the purposes of these sorts of computations. So it's basically this. This is the reason why the gradient is always perpendicular to the tangent lines to the contours. All right. Now here's another fun one. Consider the function f of x, y is equal to x squared plus y squared. Describe the gradients, describe the contours. Well, if x squared plus y squared is constant, that just means we're dealing with a circle. So the contours are actually just circles enclosing the origin. What about the gradient? Well, as we would, if we're going to assume that the gradient is always perpendicular to these contours, that means the gradient has to always be pointing in the outward direction. And indeed that is the case, because the gradient is just 2x, 2y, which always points directly away from the origin. And so we do get something which is actually perpendicular to these circles. Okay, now an actual application. Let's suppose we've got a metal plate. So it's just something lying in the xy plane. Let's say that its temperature at any given time, at any given point, is 20 minus 4 times x squared minus y squared. Find the gradient of the temperature at the point 2, minus 3. Hence describe the direction of maximal increase in temperature and the direction of constant temperature. All right, well, the gradient, which gives us the direction of maximal increase, is minus 8x, minus 2y. Well, at the point of interest, we get minus 16, 6. All right, so that's great. So that's the line of biggest increase. What about the direction of constant temperature? Well, remember that the direction of constant temperature is perpendicular to the gradient of T. So that will be useful for us in a second, but I guess for whatever reason, in this case, it seems appropriate to actually specify what this means in terms of angles with the x-axis. Using basic trig rules, we can find that the angle that this particular line makes with the x-axis is pi minus arctan of 6 divided by 16, because remember, this angle is going to be lying all the way out there somewhere. So this angle in here is arctan 6 on 16, and we've got to subtract pi from that. So that's fine. But this is actually helping us to work out the direction of constant temperature, because if we know what the angle of biggest increase of temperature is, we can just add pi on 2 to that to give us the direction of constant temperature. Well, in this case, we subtract pi on 2, but of course it's equivalent. Pi on 2 minus arctan 6 on 16 is the direction of constant temperature. Because if you take a vector and add pi on 2 to the angle, what you end up with is something which is perpendicular to the original angle you were dealing with. All right, another good one. We've got a model for the altitude of the ocean floor. So we've got some square of the ocean floor that we're looking at. And a team decides to model the altitude of the ocean floor with this particular function here, 1700 minus 30x squared minus 50 times sine of pi y on 2. I guess it's important to note that x, y, and d are all in, no, d is in meters, x and y is in kilometers. And unfortunately, since I'm introducing units, that means it's good manners to keep units in any answers you make. But first things first, what is the actual question we're dealing with? Well, the problem is there happens to be a leaking oil well at the points x equals 1 kilometer and y equals 0.5 kilometers. Finds the depth at this location as well as the direction and magnitude of the steepest increase. Steepest increase, this is a question we can answer using gradients. All right, so since x equals 1 and y equals 0.5, remember we're dealing with kilometers here. D, which is actually measured in meters, is given by 1700 minus 30 times 1 minus 50 times sine pi y on 2. Now, I'm unsure where I got this number of 250 from. That doesn't seem to be correct at all. Yeah, I think that's wrong. So it should be 1700. I don't know where that came from. Of course, that makes this incorrect, but we'll just run with it. Let's work out the gradient of that at this point. Let's hope we can actually do that. The good thing about the gradient is that when we're finding the gradient, we've got to differentiate the function. The derivative of a constant just turns to 0. The derivative of minus 30x squared with respect to x is minus 60. The derivative of this with respect to y, that's minus 25 pi times cosine of pi y on 2. But remember, y is a half, so we end up with cosine of pi on 4. If one evaluates this, you end up with minus 60, comma, minus 25 pi on root 2. Now, there are units involved here. What are the units? Well, dt on dx, this is measured in meters, and this is measured in kilometers. So this is a meters per kilometer computation. The same is true for the derivative with respect to y. Well, this isn't the whole question. We found the gradient, but we need to turn this into both a direction and a magnitude. Well, the direction can be found by finding the angle that this particular vector makes with the origin, and that can be found by taking the tangent, the arctangent of the ratio of these two things. And the absolute value, well, this is found by taking the square root of the sum of squares in there, and we end up with this ugly looking number there. 3600 plus 625 pi squared on 2. All right, so this actually brings us to the end of the entire course reader. Now, so I'll basically wrap up this lecture in the next few minutes. Now, the question is, what are we going to do next week? I'm not 100% sure, but I imagine Yoni will be getting me to look at the parts of the course reader in chapter 10 that weren't really addressed, specifically applications of gradient descent, as well as their applications to neural networks. So this is a good topic in artificial intelligence. And so I'm not 100% sure that this is what will happen next week, but I imagine this is probably what's going to happen. So with that, I think I'll end the lecture there. Since we're ending so early, please do feel free to stick around and ask questions about anything we've done tonight or any of the other weeks that you are unsure of. Yes, please do that. I think it would be a valuable thing to do. But in any case, I'll end the lecture there. Hope you had a good time. Hope you enjoy the rest of your week, and I guess I'll see you next week for the last lecture in this course. All right, thanks guys. I'm stopping the recording now.